Hello, students. Let's now talk about brightnesses and the way that we measure brightness of objects in the night sky. So a full accounting of the brightness of stars and astronomical objects in general requires an understanding of the theory of radiative transfer. We are going to deal with as a separate module. It's going to be module 5, radiative transfer. In this section, we're going to concern ourselves with basic and with historical definitions. So astronomers use a historical scale to measure stellar brightness, which was defined in ancient Greece. Magnitudes were defined by either Hipparchus or Ptolemy. Sources vary. But one of them thought it was a good idea to come up with the following scheme. The brightest stars in the sky, they said it would be of first magnitude. Stars that were not so bright would be of second magnitude. And the faintest stars that we can see would be called stars of fifth magnitude. Being a system that is divided by naked eye measurement, the scale is nearly logarithmic. It's not exactly logarithmic, but it's nearly so. So that's how our eyes perceive brightness. So as you see, the stars here that are the brightest are called first magnitude, and the faint stars are called magnitude 5. So the scale is reversed. It's a ranking system. Now, physically, what we're measuring when we want to measure how bright a star is the stellar flux, the energy flux. So the system was originally defined only for stars going from 0 to 5. With the invention of the telescope, we could measure things that were fainter than magnitude 5. So the scale was simply continued downwards, down from 5 until the faintest objects. The faintest that have been recorded would be magnitude 30, which would be an 18-hour exposure with the Hubble Space Telescope. The system is tied to the star Vega, so that Vega would have magnitude 0. And there are stars that are brighter than Vega. Brighter stars would have negative magnitude. Here you can see some reference points. Jupiter at its brightest has magnitude -2. Venus at the brightest has magnitude -4. And the Sun has magnitude -26. The full moon has magnitude about -10, -12. And in here is the energy. That's actually what you are measuring when you're measuring brightness, is the energy flux. That's the scale that is linear. Magnitude, nearly logarithmic, is a measurement of this flux. You see, if Vega has energy flux equal to 1 in arbitrary units, the Sun is about 2.5 times 10 to the 10 brighter in a linear scale that converts to magnitude -26. So the system is defined so that a difference of 5 magnitudes amounts to a factor 100 in brightness. We're going to call this quantity the flux. The linear quantity is the flux. So this is the relation that ties the system. In linear scale, the difference in flux between a star of first magnitude and a star of sixth magnitude is approximately 100. In the 19th century, it was thought to make this a standard, to fix a difference of 5 magnitudes as a factor 100 in flux. So let's derive this mathematically. If you have that a star has magnitude m1 and another star has magnitude m2, and the difference between them is 5 magnitudes, and that corresponds to a factor 100 in flux, you can derive from that the magnitude scales with the flux then according to the magnitude is equal to -2.5 times the logarithm of the flux plus a constant. So the constant is arbitrarily chosen so that the magnitude of the star Vega is 0. In this equation here, m is what Hipparchus came up with, f is the quantity that has physical meaning, and c is the constant that ties the two systems together.